So, as we discussed last time, a hybrid orbital is formed by combining atomic orbitals. Now, the number of atomic orbitals combined directly matches the number of hybrid orbitals produced. Now, the hybrid orbital has the average energy, position, and orientation of the combined atomic orbitals. So, for example, when we combine, for example, an s orbital, which is lower in energy and spherical shaped, and we hybridize it with p orbitals, which have a characteristic dumbbell shape and are higher in energy, in the end, your resulting hybrid orbitals will have the average energy of an s orbital and 3 p orbitals. So your average energy will be somewhere between an s and a p orbital. We put 4 orbitals in, so we get 4 hybrid orbitals out. And the average position and orientation of these hybrid orbitals is an average of the position and orientation of each of our p orbitals. So after hybridization, we end up with a total of 4 sp3 hybridized orbitals. And the exact orientation of these orbitals is directly determined by the orientation of our p orbitals. So hybridization, we take the average energy and orientation of each of our combined atomic orbitals. Now, hybridization and molecular orbital theory can help explain the observed bond angles and molecular geometry observed for organic molecules. The orientation of our hybrid orbitals directly influences the position and orientation of bonds in our organic molecule. Okay, so that's the link between hybridization and geometry. So let's start by looking at one of the very common hybridizations. The first major hybridization that we're going to look at is the sp3 hybridization. So in this case, we're combining 1 s orbital and 3 p orbitals. We put in a total of 4 atomic orbitals, and in turn, we get out 4 hybrid orbitals. And as we can see, the position and orientation of each of these hybrid orbitals directly depends on the position and orientation of our atomic orbitals. One thing that I'd like you to note for the sp3 hybridization is that our bond angles are equal to about 109.5 degrees. So we have a relationship between the hybridization of our central atom and the bond angles for bonds arranged around our central atom. Okay, let's look next at the sp3 hybridization from the perspective of atomic orbital theory and molecular orbital theory. So, starting off for carbon. So carbon has a total of 4 valence electrons to its name. So we're going to look at the valence orbitals, the outermost orbitals for carbon. So our outermost orbitals are our s and p orbitals. And as we can see, our s orbital is full, our p orbitals are half filled. As we discussed last time, and let's try to get some responses in the chat. How many potential bonds, how many potential orbital overlaps can carbon participate in? How many bonds can carbon form Just looking at typical valence bond theory analysis. How many half-filled orbitals do we have? We have 2. So currently, before hybridization, carbon can form potentially 2 bonds. Now, to maximize bonding and to minimize the energy of carbon's electrons, and the way that we do that is by forming chemical bonds, carbon is going to hybridize and it's going to redistribute its electrons into 4 sp3 hybrid orbitals. Now we have 4 half-filled orbitals capable of forming 4 bonds. Now, energy is conserved during this hybridization process, so hybridization isn't inherently energetically favorable. However, hybridization sets up our hybrid orbitals to form low energy bonds. So it's a step, and it's a process that we're going to think about as a way to begin to form additional chemical bonds and to maximize the geometry and energy of our bonding orbitals for bonding. Now, one thing to note, the sp3 orbitals have the average shape, geometry, and energy of the s and p orbitals hybridized. When you think sp3 orbitals, I'd like you to think relatively high energy hybrid orbitals. Why is that? Are we combining and hybridizing a large number of p orbitals? Are we hybridizing a relatively large number of p orbitals, which are high in energy? So in the sp3 hybridization, are we hybridizing a relatively large number of high energy p orbitals or a small number of p orbitals? And don't be shy to share your responses in the chat. Can you repeat that one more time?
Is it higher energy?
Yes, yeah. So we're using 3 high energy p orbitals, and as a result, our hybrid orbitals are going to be relatively high in energy. When you think sp3 hybrid orbitals, especially for later on in this class, I want you to think these are relatively high energy orbitals because we have a lot of p character. We've taken a lot of p orbitals and hybridized them together to form sp3 hybrid orbitals. So let's look at some examples for the sp3 hybridization. So let's look at how we can represent the sp3 hybridization. So first and foremost, for the sp3 hybridization, as p orbitals are higher in energy and longer than s orbitals, the more p orbitals that we have hybridized, the higher in energy and the longer your hybrid orbital will be. So just to draw out our hybridization picture once again. So we have our s orbital, which is relatively low in energy, and it's spherically shaped. The p orbitals are longer and they're higher in energy. So the more p orbitals that we hybridize, in turn, the longer and higher in energy our hybrid orbitals will be. So the more p character we have, the higher in energy our hybrid orbitals will be. That's why sp3 hybrid orbitals are relatively high in energy, because they have a relatively large amount of p character. And we'll see this when we start to look at other hybridizations. So let's keep going now, and let's look at how we can apply this idea of sp3 hybridizations to more interesting bonding structures. Let's see if we can apply this idea of hybridization to our current models for chemical bonding. So just like atomic orbitals, hybrid orbitals can overlap with atomic or hybrid orbitals to form sigma bonds or single bonds. These bonding electrons in turn are lower in energy. So in this picture, instead of our previous example where we overlapped two hydrogen 1s orbitals, this time we're overlapping a hydrogen 1s orbital with one electron with an sp3 hybrid orbital that also has one electron. This overlap in turn generates a bonding orbital that is the overlap between an sp3 orbital and a hydrogen 1s orbital. So to showcase and to draw out this orbital overlap, we draw out our hydrogen 1s, and in turn it overlaps to form a chemical bond with our carbon sp3 orbital. And as this is an overlap directly along the bond axis, we call this a sigma bond, hydrogen 1s plus carbon sp3 orbital. This overlap leads to a new molecular orbital. In this case, we have our bonding molecular orbital, and we also generate in this bonding process an anti-bonding orbital. And this anti-bonding orbital will be important later on in our discussion of chemical reactivity. Okay, so we've shown that hybrid orbitals can participate in bonding, they can overlap, and we can generate bonding and anti-bonding molecular orbitals. The reason why we hybridize to begin with is to optimize the energy and geometry of our orbitals for efficient chemical bonding. Okay, so let's keep going now, and let's start to think, well, how does the sp3 hybridization, how can we use this idea of hybridization to describe bonding patterns in organic molecules? So the sp3 hybridization is closely correlates for an atom with 4 electron groups around it, where an electron group, also known as a charged sphere or steric group, is defined as a set of bonds or a lone pair. And we'll start to understand this definition more if we think of this idea of a set of bonds. When you're counting electron groups, you're really counting the number of sigma bonds. Now, the sp3 hybridization correlates with what's known as a tetrahedral electron pair geometry. We have 109.5 degree angles between our hybrid orbitals, and the sp3 orbitals are long and relatively high energy orbitals. So let's look at 2 examples. Let's look at 2 examples for sp3 hybridized atoms. The first example we have is methane, CH4, where our carbon has an sp3 hybridization. The other example is ammonia, where our nitrogen in turn has an sp3 hybridization. Let's now unpack this example for methane, and let's try to draw out a picture for the various orbitals, the orbital energies, and how these orbitals overlap to form chemical bonds. So, first and foremost, for carbon, before hybridization, so this is before hybridization, we have a 2s orbital and we have 2p orbitals. Carbon has 4 electrons to its name. So carbon is then going to hybridize. We're going to combine our atomic orbitals to generate hybrid orbitals. So we've generated 4 sp3 hybrid orbitals, each with 1 electron. Now to form our carbon-hydrogen bonds, what we're going to do, so if we're looking at our carbon-hydrogen bond in detail, we're going to overlap one of our sp3 orbitals that is half filled with our hydrogen 1s orbital. This overlap in turn generates a bonding and anti-bonding orbital. So we designate our bonding orbital with a sigma carbon sp3 plus hydrogen 1s, and we have 2 electrons in our bonding orbital. We also, in turn, generate in this process an anti-bonding orbital between our carbon sp3 and our hydrogen 1s orbital. Okay. So to show you a little bit about what these orbitals look like. So for our bonding orbital, our bonding orbital indicates a constructive overlap. So we have an overlap between our 2 orbitals that results in the sharing of electron density between our atoms. We have constructive overlap. So we have our sp3 hybrid orbital overlapping with our hydrogen 1s orbital. And we are sharing 2 electrons as part of this orbital overlap. Now, what's a little bit more interesting is the antibonding orbital. So the antibonding orbital, or the sigma star orbital, consists of no sharing of electron density between our 2 atoms. So if we think about this from the perspective of our carbon atom, rather than sharing electron density between our 2 atoms, for our antibonding orbital, instead, if we look at our carbon and hydrogen atoms, there is no sharing of electron density between our 2 atoms. One thing that I want to immediately point your attention to is this sigma star orbital, otherwise known as an antibonding orbital. If we compare and if we impose our antibonding orbital into our bonding orbital picture, where do we note it? Where is our antibonding orbital located? Is it located on the same side or the opposite side to our bonding orbital? Where is our, it's located on the opposite side, exactly right. So we're the antibonding orbital, there's no electron density shared between our 2 atoms. The antibonding orbital is located on the opposite side of our chemical bond, and this is why many organic reactions that involve breaking single bonds, the approach will occur from the opposite side of our bond. Common examples of this would be the SN2 reaction, in which our nucleophile attacks our carbon from the opposite side to our chemical bond. So, knowing the location of these bonding and antibonding orbitals and looking at these orbital pictures can help us explain patterns of reactivity and the required geometries for certain chemical reactions. Does that make sense to everyone? So the main thing I want you to take away, bonding orbital, overlap, sharing of electrons between our atoms, antibonding orbital is on the opposite side from our bonding orbital. There's no shared electrons. Does that make sense to everyone? This is really important for later. So if there's one thing that I want you to remember, I want you to keep this in mind for later. Okay. So looking at methane in detail, we're going to draw an orbital picture for methane. So we know that for methane, after hybridization, we have a total of 4 sp3 hybrid orbitals. We have a total of 4 sp3 hybrid orbitals. So these are our sp3 orbitals. Each of our hydrogen atoms contributes a 1s orbital. Now, as we discussed, if we wanted to form a single bond or a sigma bond, that entails the direct overlap of orbitals along the bond axis. So for carbon, if we draw out each of our hybrid orbitals, so here's our first hybrid orbital. Here's our second hybrid orbital. Here's our third hybrid orbital. Here's our fourth hybrid orbital. And once we have our hybrid orbitals established, each of our hybrid orbitals has 1 electron to its name. If we wanted to form a chemical bond, just like we've seen in our previous examples, what we're going to do is we're going to take our hybrid orbital, which has 1 electron, and we're going to overlap it with a hydrogen 1s orbital. That in turn is going to form a bonding orbital and an antibonding orbital. We don't typically draw our antibonding orbital, but as you notice from the way I'm writing out my sigma bond and my atomic orbital descriptions, when you indicate and you describe a single bond or a sigma bond, you indicate both orbitals used to form that bond. Because as we notice from this picture, as I've subtly indicated, the energy of our orbitals depends on the identity of the atom, the identity of the hybrid orbital, the identity of the atom and the identity of the hybrid orbital. Okay, so we can form a bond, a sigma bond, by overlapping a carbon sp3 and a hydrogen 1s orbital. So let's do just that. So let's take each of our sp3 orbitals and let's overlap it with a hydrogen 1s orbital. That in turn will generate a sigma bonding orbital consisting of a carbon sp3 orbital and a hydrogen 1s orbital. So there are 2 ways of drawing these orbital pictures, visually and as an orbital energy diagram. This can help us get a sense of the relative energy of different bonding orbitals, and it can help us understand why some bonds are more reactive than others. So we can repeat this process for our 3 other hybrid orbitals. In which case we now have a total of 4 bonding orbitals, each consisting of a sigma bond between a carbon sp3 orbital and a hydrogen 1s orbital. So this is how you draw and label a complete orbital picture for methane. You indicate each of the orbitals used for chemical bonding, and you showcase an example of how these orbitals will overlap to form a bonding molecular orbital. Now, one consequence of the sp3 hybridization is that our bond angles, our carbon bond angles are going to be 109.5 degrees. The bond angle is a direct consequence of the hybridization and the orientation of our hybrid orbitals. Does that make sense? Any questions on this idea? Have you seen something like this before in general chemistry? Something similar to these orbital pictures?
Yeah. In mine, we barely touched this.
That's okay. We'll be doing a few examples because building off from this premise, we can start to explain more complicated patterns of chemical bonding. So, as an example of this, let's try to explain, well, why does nitrogen have a lone pair? Why does nitrogen have a lone pair? Well, as we recalled last time, the number of half-filled hybrid orbitals indicates the number of sigma bonds the atom can form. Generally, we prefer to use hybrid orbitals for bonding because they have the correct geometry and orientation, as well as the correct energy for efficient orbital overlap. So the number of completely full hybrid orbitals also serves to indicate the number of lone pairs. So looking at nitrogen, assuming it adopts an sp3 hybridization, this time we have a full hybrid orbital. And this full hybrid orbital represents a lone pair. So then, looking at this orbital energy diagram, this directly explains why nitrogen, in general, if it's sp3 hybridized, prefers to have one lone pair and it prefers to form 3 bonds. Because we have 3 half-filled orbitals and 1 full hybrid orbital. As a result, we see intuitively that one of our sp3 orbitals contains a lone pair. Now, this is important. The reason why I'm bringing this up, the reason why I'm talking about this at all, is that the energy of an electron lone pair depends on the orbital that lone pair is located. Remember, different orbitals have different energies and positions relative to the nucleus. So what do I mean by that? What do I mean by that? If we think about our relative orbital energies for a moment, our 2s orbital is low in energy, okay? So if we have a pair of electrons in an s orbital, they'll be relatively low in energy. If we think about a 2p orbital, this is a very high energy orbital, relatively speaking. And as a result, we'd expect we'd have a high energy lone pair. After hybridization, so this is just a relative hierarchy, looking at an sp3 orbital, considering and thinking about the energy of an sp3 orbital, will a lone pair in an sp3 orbital be higher or lower in energy than a 2p orbital? If we put a lone pair in an sp3 orbital, will it be higher or lower in energy than a lone pair in a 2p orbital? Lower, right, because sp3 orbitals are lower in energy. So sp3 orbitals are lower in energy than 2p orbitals. Ergo, lone pairs in sp3 orbitals are lower in energy. And just like when I told you to think, when you see the word in hybridization sp3, I wanted you to think high energy, relatively high energy. Likewise, lone pairs in sp3 orbitals are relatively high in energy. Oops, allow me one moment to scroll down a little bit. And what we're going to do next is we're going to look at different types of hybridization. And we're always going to try to pay attention to What does our bond energy look like? What does our orbital energy look like? And what does the energy of a lone pair in that hybrid orbital look like? Since our goal is to begin to start to tie this idea of hybridization to bond energy, bond length and strength, as well as lone pair electron energy. And we'll be looking at the relative energy of different lone pair electrons in chapter 2 when we discuss acid-base chemistry. Does that make sense to everyone? Does this idea of looking at the orbital energies to get a sense of our lone pair energy, does this concept, does this thought process make sense to everyone? Any questions on this idea? Yes, DNF orbitals do hybridize, and we'll talk about that in passing later on in this chapter. Good question. Now, one thing that I do want to show you is we can explain our bonding and lone pair, our bonding patterns, which indicates the number of bonds and lone pairs that each of our atoms form, by looking at hybridization and by invoking valence bond and molecular orbital theory. So for example, for oxygen, so oxygen has a total of 6 electrons to its name. So we have the 2s and 2p orbital. We have 6 electrons to work with. So when we hybridize oxygen and we decide to adopt an sp3 hybridization to maximize chemical bonding, what do we notice for oxygen? When we generate our sp3 hybrid orbitals, I'd like you to take a moment and draw out the full orbital diagram for these sp3 hybrid orbitals for oxygen, and I'd like you to tell me, how many half-filled orbitals do we see when we take these 6 electrons and we put them into our hybrid orbitals? How many half-filled orbitals do we see? 2, exactly right. We fill our hybrid orbitals with our 6 electrons, and as we can see, we have 2 half-filled orbitals, so we can form 2 bonds, and most importantly, we also have 2 lone pairs. Does that make sense to everyone? So that explains pretty efficiently why oxygen in general likes to form 2 bonds and 2 lone pairs. For fluorine, intuitively, we would expect fluorine to form how many bonds? If we fill in our orbital box diagram, if we fill in our orbital diagram for our hybrid orbitals, how many bonds would we expect fluorine to be able to form? 1 bond and 3 lone pairs. That's exactly right. We take our 7 electrons, we populate our hybrid orbitals, and that in turn lets us form 1 bond, and in turn we have 3 lone pairs. Now I just want to put an asterisk here and say that oxygen and fluorine do not necessarily need to hybridize. Oxygen and fluorine don't necessarily need to hybridize, but we can use this model to help explain the number of lone pairs and bonds formed when each of these atoms adopt an sp3 hybridization. Okay, so we have a little bit of predictive power here. We're starting to be able to explain some of the trends in bonding that we've observed and some of the trends in bond energy and lone pair energy. So just as a refresher, we can utilize and we can connect back our discussion of valence bond and molecular theory to our previously observed bonding pattern discussion, where we know carbon likes to form 4 bonds, nitrogen 3 bonds, oxygen 2 bonds, and the halogens 1 bond. Does this make sense to everyone? Does this connection make sense to everyone? Perfect. Perfect. So hybridization occurs if you need a specific orbital energy and a specific orbital geometry to form a bond. So it's both energetics in terms of you want your orbitals to be close in energy to form a bond, but you also want the orbital to have the right geometry, the right position in three-dimensional space to efficiently form a chemical bond. Does that answer your question? Perfect. So let's look. So for example, for ammonia, just to tie off this discussion, if we're looking at ammonia, we have 4 sp3 hybrid orbitals. Except the only thing that's new now is that one of our hybrid orbitals is completely full and it has a lone pair. Just like before, when we have 3 hydrogen atoms in ammonia, in order to form our nitrogen-hydrogen single bonds, what we're going to do is we're going to overlap a nitrogen sp3 orbital and a hydrogen 1s orbital, and that in turn gives us a sigma nitrogen sp3 and hydrogen 1s orbital. And as a sort of side product, as another orbital generated from this process, we generate an antibonding orbital. Just as a reminder for where the antibonding orbital is located, it is located at the opposite side to our bonding orbital. Now, we have each of our half-filled hybrid orbitals. Now what we're going to do is we're going to overlap them with our hydrogen 1s orbitals to form our 3 bonds. So this gives us a bonding molecular orbital that's a sigma hydrogen 1s plus nitrogen sp3 orbital. And as we see from our picture, this sigma bonding orbital is lower in energy than our starting atomic and hybrid orbitals. So the key takeaway for ammonia, the only thing that's different about ammonia is that we have a lone pair. And that lone pair, it's not just any lone pair. And this is where you have to be really specific. This is a lone pair that is found in an sp3 hybridized orbital on nitrogen. The orbital hybridization and the atom's identity directly impacts the energy of our lone pair. Does this picture make sense to everyone? Is everyone getting a little bit more familiar with how to draw orbital pictures? Does this make sense so far?
Yeah, roughly.
Perfect, perfect. So let's look now at the sp2 hybridization. And as its name implies, we combine an s orbital and 2 p orbitals. That in turn gives us 3 sp2 orbitals. Now, one thing that immediately should stick out to you is that the geometry of these sp2 orbitals is different, right? Does everyone notice how the direction that these sp2 orbitals are arranged in is different? And that stems from the fact that we only have 2 p orbitals this time, and as a result, our average orientation is going to be different. Now, let's unpack this next point and looking at our orbital box diagram or orbital energy picture. When we combine an s orbital and two p orbitals together and hybridize them to adopt the sp2 hybridization. So we've used an s orbital and two of our p orbitals. What is left over? What orbital is left over in this process? What is left over? Is there an orbital that is not used for hybridization? The third p orbital, exactly right. We have an unhybridized p orbital. There's a p orbital left over that is unhybridized. And this leftover p orbital is really important because it can be used to form pi bonds. Now, another thing that I want you to note, another thing that I want you to pay attention to is since we're only utilizing and hybridizing two of our p orbitals, we in turn have less p character. And because p orbitals are long and high in energy, the less p character we have, the shorter and lower in energy our sp2 orbitals are. So sp2 orbitals in general are shorter, they're stubbier, and they're lower in energy than sp3 orbitals because we have more s character and less p character. So let's just showcase that. So our s orbital is sort of short and stubby. Our p orbitals are relatively long and high in energy. So if we hybridize them together, we have more s character. So we have the shorter and stubbier sp2 orbitals. Now, if we compare this to an sp3 orbital, an sp3 orbital would be longer and it would also be appreciably higher in energy. Does everyone notice how the sp3 orbital is longer, it's less short and stubby, and it's higher in energy? Does this idea make sense to everyone? Perfect, perfect. So we're beginning to see a link between hybridization and orbital energy, and that's going to directly impact our bond energy and our electron energy. So for the sp3 hybridization, this occurs when we have atoms with 3 electron groups. The sp2 hybridization is directly associated with the trigonal planar electron pair geometry. For the sp2 hybridization, we have 120-degree bond angles. And the key thing that I want you to remember, sp2 orbitals are shorter and lower in energy. So, looking for example at formaldehyde, formaldehyde looks a little bit like this, where we have an sp2 hybridized carbon and our bond angles are roughly 120 degrees. Now, let's try to draw out an orbital picture for formaldehyde from scratch. Let's try to think about what's going on here in formaldehyde, and let's try to explain our observed bonding pattern. So first off, for carbon, in formaldehyde, our carbon, as we're starting off with, as always, we are starting off with 3 s orbitals, 3 p orbitals, and 1 s orbital. carbon has 4 electrons to its name. And in order to form our 3 sigma bonds, so we want to form 3 sigma bonds, in turn, we need at least 3 hybrid orbitals. So now, not just hybrid orbital, we need 3 half-filled hybrid orbitals. So we're going to combine, and we're going to take our s orbital and 2 of our p orbitals, and we're going to adopt the sp2 hybridization. That in turn gives us 3 sp2 hybrid orbitals, which are relatively short and stubby. Let me respect the fact that they are oriented in different directions. Okay, so we have 3 of our half-filled orbitals ready to go for chemical bonding. And left over, we have our p orbital. And this p orbital is high in energy. Now, if we just fill our hybrid orbitals with these 4 electrons, how many bonds can we form if we just filled our hybrid orbitals with these 4 electrons? Looking at this picture, we can only form 2 bonds, right? So to maximize bonding, we promote, this is known as promotion, we move one of our low energy electrons into our higher energy p orbital. Now you may say, doesn't this have an energetic cost? Well, yes, but at the same time, by generating these half-filled p orbitals and hybrid orbitals, we're able to form low energy bonds. Okay, so now that we have our initial picture for hybridization, so here's our picture of our sp2 hybridized carbon. So we have our p orbital with 1 electron, and we have our sp2 orbitals, each half filled with 1 electron each. Now, from here, we can engage in orbital overlap. So let's talk about the 2 different types of orbital overlap that we can participate in. Let's talk about the 2 different types of orbital overlap that we can participate in. So the first of which is our almost pedestrian that we've seen many times before. We can engage in sigma bonding. So that involves the overlap, in this example, of a carbon sp2 orbital. And let's show the overlap with a hydrogen 1s orbital. That in turn generates a sigma bonding orbital between a carbon sp2 and a hydrogen 1s orbital. And we also generate an anti-bonding orbital. Now to draw a picture of what this looks like, our carbon sp2 orbital looks something like this. Our hydrogen 1s orbital is spherical. And so for our orbital overlap, when these 2 orbitals overlap to form a bonding orbital, we will have a constructive overlap between our carbon sp2 and our hydrogen 1s. For our antibonding orbital, so if we think about our carbon and hydrogen, rather than sharing electron density for our antibonding orbital, there is no electron density between our carbon and hydrogen atom. So this should be familiar to us so far, this idea of sigma bonding. Is everyone comfortable so far? Does this process look familiar? Does this process start to feel familiar? Thinking about our starting atomic orbitals, how can we hybridize to form the desired numbers of bonds? What do our orbital overlaps look like? And what do our energies look like? Does this process make sense? Any questions so far? So what we're going to do now is we're going to talk about the next type of orbital overlap that I've been alluding to. So when we think about carbon, it has 3 hybrid orbitals. So this carbon can engage in 3 sigma bonds. Now, when we think about carbon's p orbital, however, carbon's p orbital can also participate in what is known as a pi bond, which is an overlap of half-filled p orbitals. So let's try to draw a picture for our pi bond to fully describe the bonding arrangement in formaldehyde. So, as we can see from our orbital pictures, we can conclude that carbon will prefer to form 3 sigma bonds for its 3 hybrid orbitals, and it will prefer to form 1 pi bond with its half-filled p orbital. Oxygen can engage in both sigma and pi bonding, forming a sigma bond with one of its p orbitals and a pi bond with its second p orbital. The hybridization of carbon directly impacts the observed bond angles in formaldehyde. This is why we observe a 120-degree bond angle in formaldehyde. Now, to fully showcase this pi bond, let's draw a picture. So we have our carbon 2p orbital that is half filled. We also have an oxygen 2p orbital that is half filled. Now, as these 2p orbitals are perpendicular to the bond axis, we can engage in 2 different bonding patterns. We can engage in constructive overlap, in which case we form a pi bond between our carbon 2p and oxygen 2p orbital. To show everyone what that looks like, we take our 2p orbitals, and if they're the same phase, they can overlap constructively to form a pi bond. Alternatively, as another orbital generated in this pi bonding process, we also generate a pi star orbital. This occurs when we have 2 orbitals of opposite phase overlapping, in which case, if we think about our carbon and oxygen atom, rather than sharing electron density, what we have is no electron density shared between our carbon and oxygen atom. This would be a pi star for our carbon 2p, plus oxygen 2p. Do these pictures make sense for our pi and pi star orbitals? They're thematically very similar to our sigma bonding orbitals, except the pi bond is perpendicular to the bond axis. Does that make sense to everyone? Perfect, perfect. Now, going back to our picture for oxygen, what do we notice? What do we notice for oxygen that's a little bit interesting? What does oxygen have? What does oxygen have? Just looking at this picture. Has a lone pair, exactly right. So it has a lone pair in a 2p orbital, and it also has a lone pair in a 2s orbital. Okay, perfect. So because we're paying attention to that, we know that the lone pair for oxygen, one of these lone pairs is found in an oxygen 2p orbital. And that has a direct impact on that lone pair's energy. Okay, so a complete orbital picture for formaldehyde is shown here. So looking at formaldehyde in detail, let's label each of our sigma bonds and pi bonds that we've discussed. So we have a sigma bond between a carbon sp2 and a hydrogen 1s orbital. We also have a sigma bond between a carbon sp2 and an oxygen 2p orbital. And we have a pi bond between our oxygen 2p and our carbon 2p orbital. And one thing that I want to highlight in our discussion, one thing that I want us to now discuss as part of this orbital analysis is I'd like us to think and let's really ponder this question. Let's really ponder this question. Would we expect these two sigma bonds, to have the same energy or different energies? And to help us with that, let's just showcase, let's just draw out what our bonding orbital pictures would look like. Okay, so when we combine our sp2 hybrid orbital and our hydrogen 1s orbital, we get a bonding orbital, right? Now, what I want you to tell me, if we have the same carbon sp2 orbital, nothing has changed for carbon. My question to all of you is, where would I put the oxygen 2p orbital in terms of energy? Would we expect an oxygen 2p orbital to be higher or lower in energy than this hydrogen 1s orbital? Would we expect it to be higher or lower in energy? Higher, yep. The oxygen 2p orbital is higher in energy. And as a result, when we engage in orbital overlap, that directly impacts the relative energy of our sigma bonding orbital. So the main takeaway that I want you to get from this discussion is that different orbitals in turn lead to different sigma bonding orbital energy. So we have to pay attention to more than just the fact that do we have a single bond, do we have a double bond, but what atoms are participating in that bond, what is their hybridization as well. Does that make sense to everyone? Okay, so these are things that you're going to see again and again and again in organic chemistry. Atom effects are very important. Okay, so one thing you really do have to pay attention to, and I have this example deliberately set up to showcase this, you really need to pay attention to the location of electron pairs. In some cases, the lone pair is in an empty p orbital. In other cases, the lone pair is held in a hybrid orbital. So, what is an example of this? What is an example of this? If we look at CH2NH, so it looks like a relatively simple structure. Okay, so if we were to draw a Lewis structure for CH2NH, I'll provide it for us, just so that way we can have a productive discussion. So here's the Lewis structure for CH2NH, and immediately the first thing that we have to try to answer is what orbital is this lone pair located? Where is this lone pair located? And if we can answer that question, we can begin to understand how that lone pair reacts and how acidic or basic that lone pair can function. So let's look at an example. So breaking this down, carbon wants to form 3 sigma bonds, and nitrogen is going to form 2 sigma bonds. So starting off for carbon, just like we've done time and time again, what hybridization will carbon adopt to form 3 sigma bonds? What hybridization will carbon adopt?
sp3.
So if it adopts an sp3, it can form 4 bonds. But we also notice that carbon also wants to form a pi bond as well. It wants to form a double bond. So then, what hybridization allows it to form 3 sigma bonds and 1 pi bond? And as I see in the chat, the sp2 hybridization is spot on. For each sigma bond, you need a hybrid orbital. For each pi bond, you need a half-filled p orbital. So if we adopt an sp2 hybridization, we in turn generate 3 hybrid orbitals. So we have our sp2 orbitals, and we have a p orbital that's capable to form our pi bond. Okay. Now looking at nitrogen, it needs to have 2 sigma bonds, 1 lone pair, and we want to form 1 pi bond. So let's look at the hybridization picture for nitrogen. Let's look at the hybridization picture for nitrogen. So what hybridization will nitrogen need to adopt in order to have 1, 2, 3 orbitals to hold its bonds and lone pairs? Let's try to get a few responses in the chat for this. What hybridization would nitrogen have to adopt? And don't be shy to share your responses in the chat. Think about our ammonia example that we did a while ago. So if we need to have a total of 2 bonds and 1 lone pair and 1 pi bond, what hybridization would we need? Keep in mind, we also need to form a pi bond. So what hybridization would we need? So we need to form 3 sigma bonds or lone pairs and 1 pi bond. What hybridization does that remind us of?
Would it be sp2?
Yes, exactly right, sp2. So then we take our 5 electrons for nitrogen and we generate our 3 hybrid orbitals and 1 p orbital. So this p orbital will be used to form our pi bond. These hybrid orbitals will be used to hold our lone pair and to form our sigma bonds. Okay, So now that we have this set up, let's draw out an orbital picture. Let's draw out an orbital picture. Let me scroll up just a little bit so that way carbon's still in view. There we go. Okay, so to start off with, carbon is bonded to 2 hydrogen atoms. So these hydrogens are going to contribute a 1s orbital, and carbon, from its 3 hybrid orbitals, will have 3 sp2 orbitals, 1, 2, and 3. So this is our carbon sp2 orbital. And after overlapping with our hydrogen 1s orbital, we'll form a sigma bond. Both of these bonds are sigma bonds containing a carbon sp2 orbital and a hydrogen 1s orbital. So we've set up the first part for our carbon atom bonding arrangement. Looking at nitrogen now, we're going to draw out its hybrid orbitals. So nitrogen has 3 sp2 orbitals. So we have 1, 2, 3. So these are nitrogen sp2 orbitals. Let me try to keep this position a little more convenient. Now, one of our nitrogen sp2 orbitals is unfortunately filled with a lone pair. This is a lone pair in a nitrogen sp2 orbital. Nitrogen is also going to form a bond with carbon, so we'll label this as a sigma carbon sp2 plus nitrogen sp2. Okay, so that's our carbon-nitrogen single bond, and it's going to form a single bond with hydrogen. That's our sigma nitrogen sp2 plus hydrogen 1s orbital. Okay, so we've described our single bonds, our sigma bonds. Let's now draw out our p orbitals. Let's now draw out our p orbitals. And to do that, I'm going to use a different color. So here's our carbon p orbital. This is our carbon 2p orbital, which has 1 electron to its name. Nitrogen also has a 2p orbital. And these 2 half-filled p orbitals will overlap, and this will form our pi bond. And we call this a pi carbon 2p plus nitrogen 2p. So we've put together all of the pieces that we've learned in today's lecture. How do we describe single bonds? How do we describe double bonds such as pi bonds? And now, from this orbital picture, first things first, does anyone have any questions on any part of this orbital picture? So just to connect this back once again, we drew our hybrid orbitals. Just one moment. We drew our hybrid orbitals by noting that to form 3 bonds, carbon would need to adopt the sp3 hybridization. That's why we have 3 hybrid orbitals. Carbon forms a single bond with hydrogen by overlapping with its 1s orbital. The carbon-nitrogen single bond is formed by the overlap of hybrid orbitals. In this case, a carbon sp2 and a nitrogen sp2 orbital. The leftover p orbital for both carbon and nitrogen is used to form our double bond or our pi bond. And as we notice in this picture, the lone pair on nitrogen is in what orbital? The lone pair on nitrogen is found in what orbital? What orbital is the lone pair on nitrogen found? It's in an sp2 orbital. Okay, perfect. So before we showcase the payoff for this discussion, any questions on how we drew this orbital picture? You will have to generate similar orbital pictures for some of your subsequent quizzes and homework assignments. Does this make sense to everyone, this procedural process for drawing out each of our orbitals and how these orbitals overlap? Does this make sense to everyone so far? Any questions? Okay, so now for the payoff. Now for the payoff. And this is going to be really cool. So, if we compare this molecule, which is CH2NH, if we compare this to something like ammonia, I'm just going to draw ammonia's orbital picture really quickly. Now, if we think about our lone pair electron energy, if we think about our lone pair electron energy, and this is where we tie this idea back to the concepts that we'll see in our chapter for acids and bases. If we think about the relative energy of a nitrogen sp2 orbital, so here's our nitrogen sp2 orbital that has our lone pair. Would it be lower or higher in energy than a nitrogen sp3 orbital? If we think about a nitrogen sp3 orbital, would it be higher or lower in energy? So an sp2 orbital, we're saying in the chat, is lower in energy than an sp3 orbital. That's exactly right. So then, what we can conclude, and this is the part that I want you to remember, a lone pair in an sp2 orbital is lower in energy. And this directly impacts the reactivity of that lone pair. In general, the lower in energy a lone pair is, the less basic that lone pair behaves. And we'll see this later on in our chapter on acid-base chemistry, where hybridization directly impacts acid and base strength. Does this make sense? Does this payoff make sense? And we can only really see this readily by drawing out an orbital diagram and clearly labeling what orbital our lone pair is located. Does this payoff make sense now? So hybridization directly impacts orbital energy, which in turn directly impacts lone pair energy. It's always better to know the reasoning behind certain rules rather than just memorizing the rules. That's why I show you the pictures. Okay, so now what we're going to do is we're going to switch gears a little bit and we're going to talk about structures called incomplete octet structures. And don't worry, we'll come back to the sp hybridization, but these incomplete octet structures are directly related to this idea of sp2 hybridization and p orbitals. So aluminum and boron, which are typical incomplete octet structures, prefer to form structures with less than 8 electrons. Now the interesting thing about these incomplete octet structures is that they have an empty p orbital that is not utilized for bonding or holding a lone pair. Now, as a result, we call chemical species with empty p orbitals Lewis acids due to their ability to coordinate lone pairs. We'll talk about this more later, but anytime you see a structure that has an empty p orbital or an empty d orbital for that matter, it has the potential to engage in and utilize that p orbital to engage in coordination or bonding events with lone pairs. And we call chemical species with these empty p orbitals Lewis acids. So it wouldn't be 100% appropriate to invoke formally the idea of hybridization for aluminum, but the way that I like to visualize aluminum chloride, the way that I like to think about it as an analogy, is that aluminum has an empty p orbital, and this empty p orbital enables aluminum to participate in coordinating and function as a Lewis acid. So when you see an empty p orbital, I want you to think Lewis acid. And we'll see a lot of Lewis acid reagents that are used to activate molecules for chemical reactions. The reason why I brought this up here is that we've already been discussing p orbitals, and the key trait for Lewis acids and many incomplete octet structures is that they have this characteristic empty p orbital. Does that make sense to everyone so far? Does that make sense to everyone so far? Okay, so let's keep going now. And let's discuss the last major hybridization, which is the sp hybridization. So in the sp hybridization, we combine one s orbital and one p orbital together to get out two hybrid orbitals. As we can notice already, we can clearly see that the orientation of our sp orbitals is different than that of the sp2 hybridization. Now, we're always paying attention to what is left behind after hybridization, and we notice that after hybridization, we have two p orbitals that are unhybridized, and these p orbitals can be used for pi bonds. So we can form up to two pi bonds in the sp hybridization framework. Further, one thing that I'd like us to note, as we are only using one p orbital and we have very little p character, sp orbitals are going to be the shortest and the lowest in energy hybrid orbitals. Keep in mind, they're short and low in energy. So just to draw a picture of this, I always like to draw pictures because it helps me remember how these orbitals are arranged in terms of energy. So after hybridization, we end up with these relatively low energy sp orbitals. They're very, very short and stubby. They very much have a lot of s character. They're low in energy. And we have left over two p orbitals. Does everyone see in my drawings how as we have more and more s character, my orbitals have been getting shorter and fatter? They look more like an s orbital in terms of shape, right? Now, I really want you to hone in on and pay attention to the energy. sp orbitals are very low in energy for hybrid orbitals. They have a lot of s character. So let's see an example of sp hybridization, and let's talk about the major features of the sp hybridization. So a classic example of the sp hybridization is acetylene, which looks a little bit like this. Thankfully, we don't have to handle acetylene in sophomore organic because it can form explosive mixtures with air. With that aside out of the way, the sp hybridization consists of an atom with 2 electron groups. We have a linear electron pair geometry with 180-degree bond angles between our hybrid orbitals. sp orbitals are the shortest and lowest energy hybrid orbitals. So let's look at another picture. And let's try to showcase carbon undergoing this hybridization process. So in this case, carbon wants to form 2 sigma bonds and 2 pi bonds. So then, starting off, we have our basic picture for carbon. So what hybridization will we need to adopt to form 2 sigma bonds and 2 pi bonds? What hybridization would we need to adopt to form 2 sigma bonds and 2 pi bonds? An sp hybridization. Okay, so we combine and hybridize our s orbital and 1 p orbital. That gives us 2 sp hybrid orbitals. Okay, so we can form our 2 sigma bonds, and we also have left over 2 p orbitals. Okay, perfect. So let me draw the p orbitals with the correct geometry, because we're starting to get towards something really important here. These 2 p orbitals have different 3-dimensional orientation, and as a result, our pi bonds will be arranged differently in 3D space. So let's look at some of the different types of overlaps that we can engage in. So first, we can form a sigma bond between our 2 carbon atoms. So to do that, we take our carbon sp orbital, overlap it with our other carbon sp orbital in our second carbon. And that in turn generates a sigma bonding and a sigma star antibonding orbital. So this sigma bonding orbital would look a little bit like this, where we have an overlap between our 2 carbon sp orbitals, while our sigma star, we'd have no electron density between each of our carbon atoms. Okay, so that's typical. Let's look now at each of our pi bonds. Since they're the 2 pi bonds that we're dealing with will be very different in terms of 3-dimensional orientation. In our first case, we can overlap our 2 pi bonds, our 2 p orbitals that are arranged on the vertical axis, and that in turn gives us a pi bond and a pi star, in which case our pi bond would look something like this. So that's our first pi bond. Our second pi bond can occur when we overlap our p orbitals that are arranged in the horizontal axis. So we have the exact same orbital picture. However, what has changed is the orientation of our p orbitals different for our second overlap? Is the orientation of our p orbitals different for this second overlap? Even though we're forming a pi bond, are these orbitals arranged differently in 3D space? Yes. So then, our second pi bond will be an overlap on the horizontal axis that looks like this. So even though we're able to form two pi bonds, the orientation of those pi bonds is different. And that's really critical, since that directly impacts how accessible certain regions of our molecule are and how accessible certain bonding and anti-bonding orbitals are towards attack and towards chemical reactions. Okay, so now that we've seen the different types of orbital overlap that we're going to encounter, let's now look at an orbital picture. Let's now look at an orbital picture for acetylene. So in this picture, we see each carbon forms 2 sigma bonds and 2 pi bonds. The hydrogen forms 1 sigma bond. So our first sigma bond involves a carbon sp orbital and a hydrogen 1s orbital. Our second sigma bond is between 2 carbon sp orbitals. Our pi bonds occur between a carbon 2p and another carbon 2p. And we notice that our bond angle is 180 degrees. Does this orbital picture make sense to you? Does everyone see each of the components that we've talked about today? Okay, now, one thing that I'm going to leave you with before the end of this lecture, one thing that I want you to think about for a moment is if we look at methane and if we compare that to formaldehyde and if we compare that to acetylene, if we think about our carbon-hydrogen bond, if we think about our carbon-hydrogen bond and we're just looking at the carbon-hydrogen bond in each of these structures, based on our orbital energy, if we compare the orbital energy for an sp3 to an sp2 to an sp orbital, we notice the sp orbital is the lowest energy orbital. So my question to all of you is, which of these carbon-hydrogen bonds would be lowest in energy? Just looking at our orbital energy. If orbital energy determines and impacts bond energy, which hybridization would have the lowest bond energy? Which hybridization would have the lowest bond energy? SP, exactly right. So in general, SP hybridization leads to, we have a low energy orbital, and as a result, we have low energy bonds. We'll focus more on this point next class session, But this is really the payoff for discussing molecular orbital theory. We can not only identify sites of reactivity and understand molecular shape, but we can also explain why certain bonds are higher or lower in energy or more or less reactive. Does that payoff make a little more sense now? Now that we've gone through and we've actually looked at each of these different bonding patterns? And if we put them side by side, does it make a little bit more sense now, that rule that you learned in general chemistry where hybridization affects bond strength? Does that rule make a little more sense now? And that really philosophically is our goal in organic chemistry. Our goal is not just to memorize a set of rules. Our goal is to explain why by invoking empirical data and chemical theory. So that's why I like this chapter. And I know this chapter 1 seems a bit long, but I'm setting up a lot of the fundamental skills that you'll need that will draw on to make the later chapters much easier. So that's it for today's lecture. So I'm just going to stop the recording.